Hello. We will be walking you through the malware project that we created for our RIT CSEC-476 Malware Reverse Engineering class. The malware we created for this project is a safe for work version of the Why Was I Breached app that was created online a few years ago. This program will generate an excuse for a data breach that occurred, and we also customized it to have sayings for specifically RIT. However, this program will be a Trojan horse. It will launch malware features when the application is closed, such as listing processes, listing system information, and uploading and downloading files via network sockets and custom data encoding so that expecting network traffic won't reveal our activity. This was written as a client-server architecture, so there is a command and control server. The client was written in C++, and the server is written in Python. The way we are going to do this is that we are going to walk you through the code review first. Then we are going to give a demo of the application. And finally, we are going to discuss how we reverse the application using IDA-Pro.
For this code review, we're going to be quickly going over the client and the server. Starting off with the client, we have our main function where we generate a seed and check for a command line argument. If the command line argument is present in CSEC, it will set the seed to 1337. Otherwise, it will just proceed into the Trojanization with Trojan Loop. Our Trojanization here takes the seed and will start printing out stuff based off of the printer function. The printer function uses that seed and uses some global variables and randomly generates some portions for it. The stuff that it fetches from are up here: the actors, methods, targets, and mitigations, and then resolutions. The generated message will be in the format here under sentence. The blank used blank to blank, but we blanked and blank, so blank. If the command line argument CSEC is present, it will use the last portion of each array, generating the message: the RIT CSEC students used their web scraper projects to crash the website, but we got Heim in trouble, and so their moms will hear about this. Otherwise, it'll be a random selection of these arrays similar to adlibs. Going back to the main function, after the Trojanization, it enters shell. Now, shell is the actual malware of this. Seeing here, we generate a socket listening on localhost because we are just running this locally. This socket opens up and listens for commands. Taking in the commands, it decodes the message and checks it against the pre-generated commands. Here the commands we have are info, lsprocess, upload, and download. The info will run the client info command, encode it, and send it back. The lsprocess will run the list processes command, encode it, and send it back. Upload will take a file and upload it to the server, and download does the opposite. All of these use the encoding that is generated. Now, our encoding takes the PR ASCII string up here, which is an array of the printable ASCII characters in Python, and then does a rotating ROT-N encoding function and decoding for this. So the rotation is the 0th character in an array that you're encoding is ROT0, the first character is ROT1, the second is ROT2, so on and so forth. This provides a nice encoding method that has the same character size as the original array, and it does have a built-in weakness where the first character is identical to what it was before encoding. For our client info command, it outputs using username, semicolon, hostname, semicolon, IP, semicolon, MAC address, semicolon, OS version. We use a variety of methods to fetch this info, starting with using get username to fetch the username. Then we use the get host name, get host by name, and inet n2a to fetch the IP address, to fetch the actual MAC addresses, and we use a WIMI command, which is sent in, and then we fetch the output of that from the buffer. And then to get the OS version, we use the various get version commands to fetch the version numbers, which are not the cleanest, but however, it is the most supported method to do so on Windows 10. For list processes here, we simply enumerate every single process, strip out the unknown processes, which are those that are backgrounded and are not currently actually doing anything. Then we send that list of processes back. When the loop completes, it just restarts again, waiting for the next command. Now, going to the server, it is a lot simpler than the client. The server simply spins up a listener on localhost port 8080. When a connection is established, it prints out, and then it lists the available args that you can use, then asks for you to enter a command. It checks if that is a valid command. If it is, it will execute that command. Otherwise, it will tell you that it is not a valid command. Now, the commands are listed in a pseudo switch case method for Python, where it checks against the string in the options struct, and if that string matches, it executes that command. Starting with info, it will first encode the string info, and using the encode command, or encode function, and then it will send that out to the client. The client will then respond with the info from the machine. The server will then decode it, split it on the semicolons, and then output using the given output that we provided. The processes, it encodes ls process, sends that to the client, then receives the output, strips it or splits it on semicolon, and then lists out the processes. And then upload and download are very simple upload and download commands that take a local file path or a remote file path, and then using the encode and decode methods will upload and download that. The encode, as before, is a rotating ROT-N. It is very simple actually to perform. For encoding, decoding is slightly more complicated. For encoding, you just iterate through every single character in the array and then rotate it based off of the printable ASCII strings. Decoding is slightly more complicated. You have to strip out the null characters, and then you have to go and reverse the ROT encoding. That is a quick review of the code of our malware. I hope you enjoyed it. Thank you very much.
I'm going to give you a demonstration of the 4 features of our malware. On the left side here, I have our Python server currently running. It's listening now, waiting for a connection from the malware that it will get in just a second. On the right-hand side, I have our malware running, and our malware, it's an excuse generator for why was I breached, and it is RIT themed. So if I hit enter, I will get a saying as to why a company or organization was breached, and what their excuse is, so I can generate as many of these as I want. However, this is a Trojan horse, so if I press any other key, this will start the malware processes. And as you can see, the malware has disappeared into the background, and I now have a command and control server on the left. So I can run 4 different options. I can check the information of the PC that has been infected by running info. And you can see you can get my username, my IP addresses, any MAC addresses that I'm using, my operating system version. You can also run pslist to get a list of the processes I'm currently running, and there are quite a lot of them. Third, I'm going to use this testfile.txt here, which contains lorem ipsum, and we are going to transfer it over the network to the location of the project directory over here. So I'm going to enter upload, and then I'm going to type the name of the file if it is in my directory. If it's not in my directory, I will have to add a few backslashes and browse up a directory. So I'm going to do testfile.txt and hit enter, and wait a minute. And now you can see that the file has moved from our project directory to the directory that the malware moved it to. And I can also re-download this file by entering the download command and then typing testfile.txt and hitting enter, waiting a minute, and the file has moved back.
I'm Connor Shade. Today we'll be going over the basics of Memory.exe. This is the program that my group wrote. So first things first, whenever you jump into the program, it's going to be seeding rand with time, so we can actually get some random printouts for the main program. Next thing it'll do is check for an Easter egg. You can actually pass in CSEC, and if you do so, you will get a nice little CSEC department-related web app inspired printout. What this does is it checks to see if CSEC was arg number 2. If it is, then it will set C to be 1337. Next thing that happens is after all of the runtime stuff is done, after a console window is acquired, it'll enter Trojan Loop. Trojan Loop is where the user sees all of the input and gets all of the output. That is the normal user of the program, not the server and the hackers who are putting this program out. So what Trojan Loop does is it'll print Trojan Loop message, and then it'll get a character, and if the character is a new line, it will enter printer, and printer will just initialize several values for essentially indexes. Easter egg seed is set. If the Easter egg seed is set, the Easter egg seed is set, a bunch of indexes will be set accordingly, and the printout will be something like RIT CSEC students used their web scraper project to crash the website, but we made a tally of stupid people on the board and got Heim in trouble, so it won't happen again. Otherwise, it'll just make a call to random, and then divide that by, or mod that with the length of whichever index it's trying to reach, and then print that out. Once the user enters something that's not a new line, they'll be kicked out, and the window will be hidden. We're doing that by passing 0 and hide window into show window. According to for the user's perspective, the window will disappear. It'll drop into shell, and in shell, it'll set up a socket. Right now, the socket is just pointing towards localhost. The server is just going to be a Python server that's running locally. Then there is some close socket on failure, just in case the socket isn't created successfully. And then we move into the actual shell loop. A loop, so long as there is a command, so long as someone's entering a command, shell will be processing. So the possible commands are going to be info, ls process, upload, and download. And essentially it's just like a stir comp. If the string matches, then it'll drop into the correct command. So we're going to go into the info command first. There is a block to set up what's going into info. And then we enter get info, client info, and client info will get the username, host name, host by name, grab the IP address, make sure it's really pretty. Then make a wmit query for grabbing all the MAC addresses. This is query here, it's not exactly hidden. After all this is done, get info will try to get the Windows version of information that get info is grabbing. It'll be throwing it onto a buffer called outstir, and it will be separating each chunk of info with a semicolon. And then major or minor version numbers and the build information of the device is grabbed. It'll pass outstir back out and drop it into command buffer. And we go all the way back up. Sorry about that, I got confused. So the return from get client info will be encoded, and after it's encoded, it will be pushed onto the stack along with the TCP socket, the buffer, the length, and flags, and that will be sent. Then we will enter the command buffer area. This will get zeroed. We'll go back up to the top. The cycle will repeat. So this process holds true for every other command. We're going to take a look at the ls process. This is just list process. It's listing every process. Same thing as before. If this stir comp evaluates to true, we enter the ls process block. At the ls process block, enter the ls process function. In the ls process function, the processes by calling enum processes. And then for each process, we are going to try to grab a handle on the process and get process information. We open the process down here, grab the base name, grab the process information, and then stir comp to check for anything unknown. And if everything turns out okay, there is information about the processes. We use stircat to put the process name onto outstir, and then another semicolon onto outstir. And this loop will happen for every process. The next functions to look at are the upload and download. First, we'll look at the upload. So essentially what happens is buffers are being created, and there are several calls to receive. We're passing in the TCP socket and then varying whether it's FN size, file name, or data size, or data. This is just kind of setting everything up, getting the correct status codes to make sure that we can actually receive the file. And if every status code, see first first FNS status, then F status, then DS status, and then D status. If everything turns out okay, we enter waiting for download block, and then after setting up the arguments, file name, we jump into download file, And then in download file, we decode the FN size, we decode the file name, we open a file in write bytes mode, right up here. If the file can be opened, we open it. If it can't be opened, we try to open it anyway. Just fopen error, print that out to standard error, and then call fwrite anyway. This is just kind of a nice little neat helper function. We already have the data to write to the file. That's passed in as an argument pointer to that data. This is just used for a nice way to wrap decoding and then writing to the file. The final piece of functionality of this program is downloading. So the same as before, if the strcomp evaluates true, we enter the download block. Here, buffers are made. We grab status codes of calling receive with both the FN size and file name. If status codes evaluate to true, we enter the call upload block because the server is issuing a download command, so it wants the client to upload something. So just like before, enter the upload file. Now step number 1 is to decode. Right, here's essentially where the function starts. We call decode, we call decode. Now we have FN size and the file name used to extract the contents of the file, and then put that into buffer. The buffer is returned. And then turned into message. Be encoded, put into message, packaged into a nice little send command, sent back to the server, and then we enter this section again. Command buffer is zeroed, and we start all the way up at the top. That is all of the functionality of this memory. Going over the encode and decode function. We're going to start off with encode. Decode is pretty much identical. The only difference is right down here, where encode has index plus I, decode will have index minus I. So this will just be a loop that will go from I is equal to 0 to I is less than 1 or 1024, and we'll increment I right down here. So setting this up, we have passed in a pointer to an array. This array is 1024 characters. This array is called dest. So step 1, we get the ith index of dest, and we set that to AL. We move AL into temp, and now we're working with that character. So for that character, we'll say it's X or whatever, we will push that onto the stack, and we will push something called PR ASCII onto the stack. Now this is a list of all the printable ASCII characters, 1 through 0, A through Z, all the other printable characters, and we will call stringchr, strchr, to get the pointer to the first instance of this string, or the first instance of this character in the string PR ASCII. That'll give us the index in our encoding function. So we move this pointer into EDX. We subtract this pointer from the offset of printable ASCII. So this way we are just getting the index. It's the pointer PR ASCII plus something, and then we're subtracting PR ASCII from it. We are left with the something. This is the index. We move it from there to temp3, from temp3 to EAX, and then we add EAX to I. This is where encoding and decoding will differ. Decoding will have index minus I. Then we move 100 onto here. We are essentially taking index plus I modulo 100. Thing from our within 0 to it'll be mapped to another part of our printable ASCII table, so we don't need to worry about it not being printable. This into CL, and then from CL we move it into destination at index I. So altogether, destination I is equal to printable ASCII character of index plus I modulo 100. So as we move through the initial buffer, I will change, I will increment, and we will end up encoding all 1024. We are going to hit this path. We have hit all 1024. So we push 1024, we push dest, dist and dest. We stir copy them together. We end up with everything in DEST, which if you look up here, that is a pointer that we passed in to this function. So we don't need to pass anything out of it. Now, decoding is going to be pretty much the same thing. Technically, we still have dest, we still have AL, we're still passing things between temp2 and temp3. And then right down here at the bottom, the only difference is we are subtracting EAX, which EAX is temp3, temp3 is the offset. We are subtracting the index from I, or I from the index, sorry. We are then moduloing that by 100. So that is encode and decode.